Hello everyone, welcome to Learning Express YouTube channel. So friends, today in this video, we will continue the frequency response of 5 transistor OTA. In the previous video, we have seen this frequency analysis on the level of control sources where we have used the GM cell continuously and after that analyzed the frequency response. And later we have seen many things in the frequency response including body plot, phase and magnitude plots. Okay, so again we will back on this five transistor structure, which we usually name as the five transistor OTA. So I have means drawn two structures here. One is simple five transistors and one capacitor load, and other structure is this five transistor structure itself is replaced by a GM cell, which we are discussing thoroughly till now. So ideally, if I'm considering both the cases, let's say the output impedance of this GM cell is infinite, then what we have seen, if we have seen the cell is ideal, this GM cell is ideal, then what should be the transfer function actually? Okay, so we are seeing that there is a current generation which is nothing but I is equal to GM V in. Okay, so from here, what was the voltage? Voltage was this current was charging the capacitor. So in the frequency domain, this current divided by this, sorry, the multiplied by impedance of capacitor, which is nothing but Gm by CLS V. So what was the transfer function coming here? So ideally, it is a proper integrator, which is the expected, which is our expected target. So what is the UGB? UGB here is GM by CL. For any GM cell, its output load means its own GM divided by output load is nothing but a UGB. Decide the speed. Okay. So here also, what you see, this they both are the equivalent structure. So GM is actually which is nothing but GM of one or two transistor. I am considering that GM of one equal to GM of 2. So these both structures are equivalent. You can see the output means for this structure we can see the GM is nothing but GM1 or 2 because both are equal. We have seen it. Okay. So what we can see, ideally if I'm considering output impedance to very high, we have simple one pole which is at origin, which is the actual target. This is nothing but an ideal structure or ideal GM cell or ideal op amp where we have no output impedance and we have a proper integrator with the UGB of GM by CL and the gain of infinite. This is our target we have seen many times. So what is the target? Target is our gain to be infinite. It is not actual target, but yeah, it is an ideal behavior of this op amp. For the ideal case, the error is 0. This we seen already this thing, and closed loop gain was coming out to be 1 upon beta, where we have seen these things in detail. Okay, so now I will specifically discuss about this 5 times OTA structures, and we will see how to calculate different poles and zeros in the non-ideal case. Okay, so let us see. So what we know that practically we don't have infinite output impedance for this 5 transistor structure or this GM cell. Now we'll see exactly where is the pole and zero in this structure. This transistor I am not biased at VB not. So first we will see what are the possible nodes. From those nodes we will see this, what do you call, the poles first. Okay, so this is the node where there are other capacitors also apart from this cap load. Other node is this, and third node is this. So actually in this structure there are three nodes possibly because this is shorted, so this node and this node has the same cap. Okay, so what do you see? We'll first see the pole calculation for this structure. Pole calculation. So first of all we should understand what is the definition of pole. The transfer function should be infinite, or I will say V out should be infinite. Okay, so V out infinite means we have seen other way. If I am making R out or Z out, to be infinite, then I can have the V out to be infinite by considering some finite I out. Okay, then we can see our V out is infinite. So this was one way. Other way was, first we will see the pole and no, sorry, we will see the equivalent capacitance. What do you see? Equivalent cap and resistance particular node. One more thing, nodes should be non-interactive. Poles contributed by all the nodes should be far apart. Then only we can say this particular system is or particular node is contributing to the pole, and this pole can be calculated individually or independently if there is no interaction mean to say I will consider one example that I already mentioned. Okay, if there is a RC circuit, let's say this is a R and this is a C, a simple pole will come from pole flow. The pole for the system is what? It is nothing but tau equal to RC. So the pole frequency is your 1 upon RC. Okay. So if I am connecting another RC structure, so what is the pole for this structure? It should also be 1 upon RC. If they are two independent structures, let's say there is an interaction between them. Now the current which was charging this cap is not exactly what was previously. Now these are the two currents which are summing up to this current IR. Previously this IR, let's say this is I1. Previously this I1 was completely flowing through this capacitor. Now this I1 is split into the two parts. So there is an interaction between two RC cells, and now it will not individually contribute to the poles, pole 1 and pole 2 1 upon RC. Rather there will be the equation, which is a second order equation, and we can only see these two poles individually 1 upon RC when these are far apart. Otherwise, there will be some second order equation and we have to solve that equation to get the individual poles. So directly we cannot say that RC is a time constant for one section and for the second section, because there is an interaction now. Okay. So if there is no interaction, then we can have the two individual poles. Rather, I will say if there is a buffer which is means restricting the current flowing. If there is a buffer, then there is no current flow from one branch of the RC to other. So I will say this is a buffer gain equal to 1. Okay, in that case there is no interaction between the two RC sections. Overall we can have the individual RC time constant, so individual poles associated with. So now let me have to see this 5 times 2D structure, and we will see poles and the zeros. Okay, so when we calculate the poles, I'll consider all these independent sources to be 0, input to be 0. Okay, this is the CL. So there were two methods while we were calculating the pole analysis. All these are 0. That one impedance is this is my, I should say, R out, and this is CL. So overall structure I can have what? This R out, they grounded to 0, or means it is grounded. After that CL, so it is simple RC structure, or some source was there and we have grounded it. So overall I can say this is nothing but a RC section, two parallel. This thing I told you previously. Let's say this is my Z1, this is my Z2. To make my output to be infinite, the only thing is make the R out to be, or Z out to be infinite. What mean to say? What is the Z out for this structure? Z out for this structure is Z1 Z2 by Z1 plus Z2. So making Z1 equal to minus Z2. This thing we have seen already many times. Okay, so it simply means Z1 is what? R out. What is Z2? It is nothing but 1 upon CLS. So overall S equal to minus 1 upon R out CL. So pole frequency that I am getting from this load is 1 upon R out CL. This is the pole frequency we got from the pole. means from the load side. Okay, so simple calculation, we will stick to the fundamentals, that what is the way we have seen. This is the fundamental where we can have two impedances, Z1 and Z2, they are connected in a parallel, and we have to make the output impedance to be infinite, because we have to make anyway V out by V in to be infinite, which directly means V out to be infinite, which directly means R out to be R out slash Z out to be infinite. So these are the things we have to apply fundamentally. Okay, so this is the one pole we calculated here. So what is the R out for this structure? This structure R out. Now you see R out calculation. Okay, many of you may have direct answer for it, but I'll go for the calculation because some people already told me to go through the proper calculation. Well, where there is a possibility, I will take a shot. Otherwise, there is a proper calculation for it. Okay, so now I will consider the structure. So we will have the R out from this point. We'll calculate R out from here. What are you going to do for that? We will apply a test voltage source, and we can observe this current. This is the one method. Apply a test, apply a test voltage and measure the current. One method. Second method is apply the current source and measure the. At present, I am considering no other capacitor because we are only focusing on the load capacitors, and from there we are seeing what is the pole contributed by the load only. So all other possible caps from other nodes I am considering to be not present there. Okay, so other thing was to apply a current source here, to call IT, and measure the voltage VT here. So in this case, what will be the R out? VT by IT. What in this case? Here also R out is VT by IT. Okay, so both the cases we know. Let's see from this structure or the second case. You can use the first case as well, but I am taking the second case. So yeah, there is a IT going here. I'll consider all these things, means I mean to say I'll consider lambda 2b not equal to 0, which is very important because without that we cannot say what is the impedance at these upside and downside. And other thing, I will consider the body effect as well. Okay, body effect is considered as well, or we can ignore it also, but I should make this statement here. Maybe for the first time calculation I can avoid it, and later we can consider it. Okay, so this is the current which is entering into these two transistors. This is my M2, this is my M4. Okay, this is my M2 and this is my M4. Yeah, this current IT has two paths. So now point comes, what will happen to this side current? This side current, let I should change the color. This side current will copy exactly here because they are the mirror. And what will happen? And this side current, there is this side current, this side current. So this side current had two paths from this node. Let this node call X. This is one path and this is second path. So what do you think exactly the current generated in this M2 will go on which side? Actually, if we see the effective impedance looking up for the transistor M1 is much lesser than the looking down impedance of transistor M0. Okay, because I will say looking up impedance R up from the source of M1 is lesser than, or I would say much lesser than this R down from drain of M0. And we can see also what is happening for the M0. M0 is this structure, and after that some sort of load is connected here. If I'm just considering that this my M3 is offering a load of, let I call 1 upon GM3. What should be the up impedance here? R up for 1, we can see it directly. What it should be ideally, it is nothing but 1 upon gm when this there is nothing connected to the drain terminal. But for it, we can see this calculation also. Let apply a test voltage here. This is I doing a separate calculation for it. Okay, and let I consider it R. So what should be the this is my IT, upside is IT, and this is actual ID I always consider. So what is the ID? ID is equal to minus IT is equal to GM VGS. What is the VGS for? Gate is grounded and source is at T, so it is minus VT. GM VGS plus GMV VB. Body is also, I would say, body voltage is also ground. Okay, so GMB BBS. So ground means body minus source. So source is at VT. What about GDS component? GDS. Now VDS. What is the VD? VD. This is drain voltage. Drain voltage is nothing but IT times RD. IT RD minus VT. This is the complete expression that I am getting for here. So I'm just looking up impedance. I'm just calculating the looking up impedance of transistor M1. So what is this? Minus IT equal to minus GM. Okay. Sorry. Let me clear it. So what it is? It is minus VT GM plus GMB plus GDS plus GDS ITRD. Okay. So let separate the components. I take IT on this side and BT on this side. What will happen here? IT 1 plus GDS RD. This GDS of the same transistor and RD means that is 1 upon GM3 equal to BT GM plus GMB plus GDS. Okay. So what is the looking up impedance that I'm getting? VT by IT is nothing but 1 plus GDS RD divided by GM plus GMB plus GDS. Now I'll take some assumptions because this is my actual calculation for this looking up impedance of the transistor M1 only, which is lying here, because we are interested in this is the looking up impedance which I call RUP, which I am calculating at present, called RUP. And at this node, other transistor was my M0. And for this, I was very much clear that it is nothing but R down is GDS inverse of 0, which I call RDS of 0, which I am very clear. So these two the things will give me what current splitting is happening here, because this is the current that is coming from the transistor M2. So yeah, this is nothing but the current generated in the transistor M2. I should say I2. This has to be split into the M1 and M0. Okay, this has to be split between M1 and M0. Just remember the structure what I am telling on the previous page. Okay. Yeah. So RF. Now I'll assume some assumptions that GM is much greater than your GDS, and GM is also significantly greater than this GMB. So from these two assumptions, what can be my RF? My RF is 1 plus GDS by GM3 divided by GM of 1. Okay. It's a GDS of 1. So okay, RDS. Yes, now. So this is my GDS of 1. So what can we see here? Now let do. So here we can see this GDS of 1 is also much lesser than the GM3, because GM is of some higher order thing and GDS is also very low. Okay, because GDS is nothing but RDS, which is always of some tens of hundreds of kilo ohms. Due to this, GDS comes with a few millivolts or microsiemens, sorry, not millivolt, so a few microsiemens. and the GM actually comes in the millisiemens also. So ideally we'll consider that. Okay, so ideally what is happening here, this is approximately coming as 1 plus 0 nearly by GM1. So overall this is nothing but, so looking up impedance here at this node, I'm saying that it is 1 upon GM1. Okay, so what looking up impedance we are seeing here for this device, 1 upon GM. Don't say directly that the looking up impedance for this device is 1 upon GM1. Okay, it nearly comes as fine, but for for that particular thing to tell, you must have the proper calculation here. This is a proper calculation that we can go without writing any small signal model. Okay, so these are the equations. Just you should remember the node voltages. What I considered here, because I know the direction of the current, I always consider from drain to source, whether it is a PMOS or NMOS. So I have considered from PMOS, means drain to source of this current is ID always, which I call, so ID here in my case assumption where I assume this VT test source is minus IT. So from there, what is the GM? What is the first current component? Because ID, that this thing I should mention here because some people might have some confusion here. Okay, so what is the general ID? The general ID has the equation component. I will write here ID S always has the component GM VGS plus GDS BVS, sorry, GDS BDS. So these are this is a standard equation that we should always follow without considering the small signal equation. So GMV BVS. And here we know all these values, what is the gate voltage value and what is the source voltage value. So from this equation only I have written this particular in this single line, and after that we have calculated it here. Okay, and these are the few assumptions that we should always consider, and approximately you can say the looking up impedance 1 upon GM. And what to speak of the looking down impedance, nothing but a RDS of this transistor M0. So what we can say from here, we can say R down is much greater than R up. So whatever the current coming from the transistor M1, sorry, what current coming from transistor M2 is going completely toward the transistor M1. Okay, this is my M1, this is my M0. So completely it is folding back. So here I applied actual test current source because I need to calculate output voltage, sorry, output source, output, what I say, impedance. Okay, so one current component was going up. I'm not, I'm just, I'll calculate it, just it. Okay, so let, here the component was coming as I2, this is my M2. So it is completely flowing this way. So it is completely going to this way, I2. Okay, so what I should say here, if I2 is completely going here, and here is the mirror function, so I think due to lack of space I will go here. What is happening? So let us see this thing very properly. Don't confuse that why I'm applying IT here. You can apply VT also, and you can observe the IT. So because I know that IT current is a sum of the two currents, let I call it I4, let I call it I2. So overall IT is the sum of I2 plus I4. So now what is happening here? I have seen that when this I2 current is coming here, it is going nearly to 0 amp. I will consider here, and completely it is going this way. Okay, so this current I2 is going this way. It is also flowing through the I3. So what is happening actually? It is copying, it is mirroring here. So it is coming here as a I2. I2. Okay. So what is exactly happening here? This I2 and this I4 and this I2. So overall, what I am seeing, what actually I am seeing is not the current which is going out of this transistor M2. Actually, it is also taking one more component which is I2. So I should say 2I2 plus I4 is the total amount of current going out from my the source. Okay, 2I2 plus I4. What we are seeing, how it is coming at 2I2. So now let me consider what is the I4 and I2. Okay, these are the two values I have to see it for it. Okay. So one component of current is what? And that is I4. I should first tell you what is the I4. This is anyway ground. Here what we have some sort of voltage which is VT. Okay. So one component of current is this, and what to speak of this voltage, gate voltage. Okay. So as of now, I'm not worrying about the gate voltage because gate to source is applied here. So that component of current I am not worried about here. I'll see what is a dominant impedance looking up. For this particular M4, the impedance looking up is what? Let I should say RF4 is severely RDS4. Okay. So what is I4 exactly? I4 is nothing but BTY RDS4, which I can also call it GDS4. So this is the I4 current. Now what to speak of I2? Because we have this structure for the I2. Here one transistor, here other transistor. And this is grounded. And this potential we have VT. Okay. So now what is happening here? One thing that I should consider here. This impedance we have seen that I should replace with the impedance. It is nothing but RDS of 0. And here effectively I have seen RF which is was nothing but nearly 1 upon GM1. Okay. So at this node which I call X here or X. So at node X I have two impedances. So effectively what I will see this transistor M2 is like this. So this is my VT. And overall, what is the effective impedance as a source? That effective impedance at source of M2 is 1 upon GM1 parallel to RDS naught. So what should be? It should be nearly 1 upon GM1, which is smaller. So it should be the effective impedance 1 upon GM1. So what you can see here, we can have all three components. Let I call it, this is my I2. Okay, I2 I want to calculate. Okay, so I can have a body effect component and means other component here as well. Okay, so what is the current actually I should write here? If I want to calculate effectively the looking down impedance for this transistor M2, then I can see exactly what is happening here. Okay, so what is happening here I'll see it. Okay, so for this structure, let me calculate the effective impedance looking down, and from that impedance we can directly say what is my I2, because the I2 will be like, it will be the function of what, VT, and R drain, or R, I should say R down. It should be the function of this only, because I2 is nothing but VT by R down 2. So first I'll look for the R down 2. So yeah, this is the M2 transistor. So this particular impedance looking at this node, I am calling it R down 2. That I should change the color of the pin so there is no confusion. At this node, I am saying it R down 2. Now we have target to calculate this particular distance. So till now we have seen effectively what is happening with this transistor M2. At source, I have seen effective impedance, which I also call RS as of now, which is nothing but 1 upon GM1. And this node I have VT, and here I have I2. Okay, so what is the I2? I2 is nothing but GM2 VGS, because I2 and IT of 2 has the same direction. IDS2 have the same direction because drain to source. So I will write the same equation. So first of all, I should write what is the source voltage. Source voltage of 2 is nothing but I2 times RS, where RS is 1 upon GM1. I am not writing here. So what is I2? I2 is GM2. What is the gate? Gate is 0. So it is minus uh, I2 RS. Same for GDS component, because what is your drain here? Your drain is at VT. What a source is at? Source is at I2RS. What to speak of body? Body is I call 0. And what to speak of source voltage? It is nothing but I2RS. Okay. So let me club this I2 component one side. 1 plus GM2RS plus GDS2RS plus GMB2RS equal to GDS2BT. Okay. So I should say this is fine now. Okay, I think, is there anything missing? No. So I2 is equal to what? 1 plus GM2 plus GDS2 plus GMB2 RS, and where RS is my 1 upon GM1, I'll replace it GDS2. So what should be the exact expression here? Now, let I call. Okay, I should find here I2. I2 is nothing but BT GDS2 divided by, what is this here? 1 plus GM2 RS. I am ignoring GDS term and body factor GMB GMB2. Okay. Just I have written there so that you can have the clear idea, but later I have ignored it. What is I2 I am getting? I2 I am getting BTY DS2 1 plus GM2 by GM1. This is the I2 I am getting. So is there anything here and there? So what you can see from here, one more assumption for this 5 transitor structure is GM1 equal to GM2. So what is I2 actually? I2 is BT by RDS2 into 2. This is 1 of, so 1 plus 1 2. So overall I have I2 as BT by 2 RDS2. Okay. And what is the I4? BT by RDS4. So what is the exactly R out now? R out now BTY IT, where IT is what? I2 plus I4 plus I2. Remember this thing. I already have written this thing on this page. 2 I2 times I4 comes. Generally we say that I2 plus I4 is equal to IT. Remember this thing. This is a very in-depth analysis. You have to see this I2 folds back and it is giving me 2 times I2. Okay. So overall, what should I say? Okay, instead of solving this equation, I should say my IT is 2 times I2 plus I4. 2 times of I2 is what? BT by 2 RDS2 plus I4 is BT by RDS4. So here this factor of this means, yeah, this factor of 2 is cancelled here. So in generally it looks like that this R out is nothing but parallel of RDS2 and RDS4. It ideally looks like what ID equal to IT equal to VDS GDS2 plus GDS4, or I should say R out is GDS2 plus GDS4 reciprocal, or 1 upon RDS2 parallel with, sorry, missing So this thing we generally see it. It is not as simple as straightforward as we know. So it is nothing but RDS2 parallel RDS4. Okay, so this is exactly what is happening in terms of currents there inside this structure. You can see and analyze it, and after that what we can see from here, the pole is nothing but the pole is R out times CL. Okay, so now we can easily see what is the pole. We have seen the pole frequency was nothing but 1 upon R out times CL. So what is my R out? R out is nothing but RDS2 parallel RDS4 and CL. So what we know, the CL is also large because it is a load cap. Sorry, it is a load cap. Large because of load cap. When we drive any second stage with this particular structure, usually we see that this is a large, particular large stage. Okay, so this CL is large, and also this is a large quantity. RDS2 parallel RDS4 is also a large quantity or is a big quantity. So overall, what we can see from here, the omega PL that we have calculated at the load is nothing but is contributing to the dominant pole, because both new terms in the denominator are large, so it contributes to the very small frequency which is called the dominant pole. Okay, so till now we have seen how exactly we are calculating the output impedance at this for the 5 transistor OTA structure. Later, when will be analyzing the other things here, like your zero at the mirror terminal and after that pole at the mirror terminal, then we will see exactly this analysis is very much helpful. We should have the understanding of each and every node impedance. We directly should not say that this is 1 upon GM. That is a better thing to tell with the intuition that this is 1 upon GM, it is a RDS only. But let me tell you one thing, what exactly happening with the current components, we should always remember these things in the mind. And after that, we should proceed with the calculation. There will not be any mistake. And this is a rigorous way of analysis. Later, you can directly use your intuition that the pole at this node, or the output node, okay. So this is the rigorous way of analysis. Later, you can directly means directly you can use your intuition that it particular what is happening here at this node. Okay, yeah, you can directly say that this is the node, the capacitance at this node, and this is the impedance. When we look from the outside, it generally comes as the impedance, parallel impedances of these two. But ideally, what we should see, when this should be the parallel impedance of two. Okay, let me clear one thing. We directly say that it should be the parallel impedance of these two transistors. But ideally, I should say this particular statement is correct, exactly correct for this thing. Okay, that I should say, yeah. When we connect a particular structure, that I should say here, this is my M4. It is biased so to grounded. This is my M2. It is biased just some potential, so it now ground. So when we look from this terminal, if I am looking to R out, then it can be directly said that it is nothing but a parallel of these two impedances. Directly we can see it. And we can say it. But these two structures are different. But still we are getting that. Still we are getting the same. So this is the complete analysis you can go through. That even there is a complex structure under M2, but we are getting the same of means nearly of the same order. We are getting the impedance of the same order. And after that there is something on this top that we know is a mirroring. Okay, so what we can see, this particular structure and these two structures are not exactly looking same. Even we are getting at the output, the impedance looking here is RDS of 2 parallel RDS of 4. So this is the beauty of this analysis. You can see even after this much means this much complexity at this even after this much complexity at the source of the M2, we are getting the same output impedance. Okay, So this is the beauty of the analysis. That's why I went through this analysis. So even after this structure, what we have seen, we have just seen the effective impedance of this node and what is happening with these current components effectively. And accordingly, we've seen that this is the output impedance. What we are getting is the same for this structure. But directly saying that output impedance for the 5 trans 2T structure IDS2 parallel IDS4 is not a good and judgmental statement, because we are seeing that this thing directly can be said for this structure 1. Okay, this thing is saying directly good for structure 1 but not directly for the structure 2. Okay, it is not as symmetric as we are seeing it. Okay, as we are saying, it is not that symmetric. So structure 2 is not that symmetric, but still we are getting the same. It's a good. So you should go through the analysis again. And I think this is enough for this video. In the coming video, we'll see exactly the calculation of mirror pole and mirror zero, and then we'll write the overall transfer function. And this pole is contributing to the dominant pole, and later all the poles and zeros, whatever we will get, will be not dominant because they will be coming from the parasitics only, and this is coming from the load. That's why it is dominating, and these all will not dominate structure poles. Okay, so I think this is enough for this video. Thank you.